Hi everyone, welcome to my video lab report for Lab 5, Choose Your Own Adventure. For this lab, I've decided to track the motion of a falling monkey with a parachute. For this week, I was traveling a lot and did not have access to many materials that may have been strong demonstrations of physical principles. I decided to browse through the tracker files and found a funny video of a monkey falling with a parachute that I wanted to learn more about. This lab is a great representation of Newton's second law, which I have written in the velocity update format here. It's also a representation of the energy principle, where the change in energy of the system is equal to work, potential energy, and temperature change. Here, I will be ignoring the change in temperature because this information is not included in the video, and it is safe to assume that this change would be negligible. Potential energy will be attributed to changes in gravitational potential energy, and W is the change in kinetic energy. Important equations in this lab were the equation for drag force, gravity, and net force. For this lab, I will be using several computer models that account for different forces in order to predict the motion of this object, comparing this motion to that of Lab 2, where there was a falling object with no parachute. The purpose of this lab is to use physical principles that we have learned throughout this course and apply them to a system that we can analyze using Tracker and GlowScript. I have decided to analyze the motion of a falling object with a parachute and comparing this model to my results from Lab 2 to see how a parachute affects drag force. Here you can see the toy monkey falling with the parachute. It is clear that shortly after the parachute opens, the system reaches a terminal velocity. I analyzed this video in Tracker and found that the system did, as I predicted, reach terminal velocity, as you can see here by the straight line towards the end of the run. In GlowScript, I modified the code from Lab 2 in order to predict the motion of the monkey parachute system with only the force of gravity acting upon it. This model did not predict the motion well because it overpredicted the total distance traveled in 6 seconds. The lack of an opposing force to motion allows the object to travel further in the same amount of time. I then modified the code to predict the monkey parachute system better. The addition of the drag force slows the object down, and the magnitude of the drag force constant B is determined by the mass, density, surface area, and other factors of the object. The end position of this model was almost identical to the end position of the tracker data, thus this model is much improved. Now, I would like to compare these results with the results of Lab 2 in order to better understand the effect of parachute on drag and net force. The model without drag for the ball lab is also a poor prediction of motion because there is no opposing force to slow the object down to a terminal velocity. Thus, this model predicts that the object travels much further than it really does. The model with drag predicts the motion of the system well, much like in our monkey parachute system. Here you can see that the system does reach a terminal velocity. For the what-if questions in this lab, I would like to compare the drag coefficients of the two systems. For both labs, I used the guess and check system that was shown to us in the lab instructions of Lab 2. The drag coefficient of the monkey parachute system was 0.49, while the drag coefficient of the paper ball system was 0.0015. These results make sense because the addition of a parachute should add more drag to a system. This is the purpose of a parachute. A larger drag coefficient multiplies the velocity of the system by a larger magnitude, giving a larger magnitude for drag force, as shown in the equation here. The drag coefficient is affected by the geometry of the system as well as the surface area. The surface area and geometry of a parachute are more ideal to increasing drag than a ball without a parachute. I would also like to talk about how a parachute can affect terminal velocity. It seems from this lab that the addition of a parachute allows the system to reach terminal velocity quicker. The system and prediction are not perfect, however, because we are oversimplifying the mechanics of a parachute in this lab. It is reasonable to assume that a person falling with a parachute would reach terminal velocity more quickly than a person without a parachute or with a broken parachute, which would not be good. This is why skivers use parachutes that are always intact and double check. Thank you for watching my video lab report.